I'm back. I've had a few emails come in, I don't know how, but they did, and from students asking, wanting some clarification on questions about figuring out unknown structures from the NMR spectra. Now, if this was the face-to-face version of the class, I would probably have used, every professor's secret weapon, read the book, and gone on and counting on the fact that it would probably take the students a good week or two to realize there wasn't a book in the class, and kind of chuckling on my way and get on with it. But we don't have that option here. I could still say read the book, but again, we don't have one. And being a summer class, I certainly have plenty of other important things to be doing right now. But I decided to go ahead and, in a class where the students have to watch some of my crappy videos, that the answer to the problem was to make another crappy video. So here I am. What I'm going to do is go through a couple of the unknowns on the Friday assignment for the chemical shift module, the one we're in right now. And what I wanted to do is go through the spectra and try to demonstrate for the group how I look at a set of spectra and try to determine the puzzle pieces, the pieces that I have to think about when I'm trying to put together a structure. I'm not going to solve the structure completely because, let's face it, what would be the sport in that? But I do want to kind of essentially come up with an inventory of pieces and clue you in onto the things that I look for. Now, some of you are pretty good at this already, and that's great. Some of you have had decent enough experience with it. Others may not have seen much of this at all. So, this is for everybody in the class, but certainly for folks who might, be struggling with, how do I begin actually determining these chemical structures. So, looking at the set of spectra for the Friday assignment in the chemical shift module, and they're on the course website right now, a collection of PowerPoint files. There is a collection of spectra for what I call basic alcohols, and we're going to leave those. I'll leave those for you guys to work on. But I do want you to look at the set of spectra labeled the basic unknown. And you have no other information about this thing other than it's an unknown molecule, no formula or any other thing like that. We get into a later module in how we use formulas and sample histories to help us with our structure determinations. But for right now, this is all we have are these pieces. So what I usually do when I'm confronted with an unknown like that is I start doing what we've been doing in class so far. Start taking an inventory of the pieces. And so looking at this one for a moment, I am going to take a look at the number of hydrogen groups. Okay, number of hydrogen groups in this thing. And looking at it here, there seems to be 5 groups. And they are in a 2 to 1 to 2 to 2 to 3 ratio. Seems to be a total of 10 hydrogens in this molecule. And remember, that could imply 10 hydrogens, or it could imply a greater number if the molecule has a significant amount of symmetry. But we're looking for certainly at least 10 hydrogens in this thing, because these are all the smallest whole number ratios possible. Then the number of carbons, okay, and the number of distinct carbons, okay, carbon 13's in here. We seem to have, yep, there it is, 7 carbons, 7 distinct carbons. Now there could be more, of course, than 7 carbons. There's at least 7. There could be more if the molecule has any symmetry. So just looking at the number of peaks and their integrations for the proton spectra, this is what we have. Our new tool in the toolbox is the chemical shifts, and it's a very powerful one. And so now I start looking at the chemical shifts. Of course, remember, we're trying to learn how to drink from the fire hose of information. We take this very piecemeal, one bit or set of information at a time, and then start putting things together. And the chemical shifts for this thing are very useful. Notice that these 3 protons in the molecule are at chemical shift range. We have 5 hydrogens at 7 to 8 ppm. Okay, 5 hydrogens, 7 to 8 ppm. Oh my goodness! I mean, there's just no way that these spectra could scream any more loudly than to say we have an aromatic ring with one substituent on it. Okay, so remember, there's something here at that position. It's not a methyl group necessarily, but there are the 5 carbons, or there are the 5, hydrogens, the ortho and meta positions integrating to 2, the para position integrating to 1, 5 total. And to confirm that, you can now switch over to the carbon spectra, and sure enough, you see 4 carbons at 120 to 140 ppm, which is exactly what we would expect to see from an aromatic ring like this. 1, 2, 3, 4. Okay, the aromatic ring has its symmetry. So the ortho and the meta positions are, 2 different carbons, but 1 group each. And so that, we have beautiful evidence, irrefutable evidence that we have this aromatic ring in the molecule. So this, and I'm going to go ahead and reproduce it over here, is one of my puzzle pieces. And I know this absolutely. Okay, there's no question about this one. Okay? All right, looking at some of the other things here. I see 2 hydrogens at, and let's see, the exact value that I got looking at Spectra was 4.3 ppm. Okay, 2 hydrogens at 4.3 ppm. Almost certainly then, this is the distinctive chemical shift range of protons. Did I write a 3? That was stupid. CH2 group near an oxygen. Okay, I mean that range around 4 plus or minus about a half ppm either way is very distinctive for oxygens and ethers and esters and alcohols, those types of functional groups. So we certainly have a CH2 group, extremely likely have a CH2 group next to an oxygen. Again, combining this information with the carbon spectra, I do see a carbon at, and this is about 60 ppm, yeah, about 60 ppm, which could well be that, CH2 group. Okay? So I'm going to add to my collection of puzzle pieces that fragment here. And then I see 3 hydrogens at 1.3 ppm. Okay? Now, 3 hydrogens at 1.3. It can't scream much louder that has got to be a methyl group. Okay? And the other thing about that methyl group, at 1.3 ppm, right down there near 1, that's likely at the end of a chain. Okay? In other words, it's not a methyl group on an oxygen or on a carbonyl or on something interesting. That's usually a methyl group, CH3, CH2, CH, at the end of a chain. Okay? And sure enough, in the carbon spectra, we also see a carbon, and this one was at, let me get the number here. I should have written that bigger, I suppose. Oh, about 12 ppm. There you are, at about 12 ppm. Okay, and so clearly CH3, where this area over here is at the means we have an alkyl chain. Okay, here, not a CH3 next to an oxygen. Finally, there is one last peak we have not talked about, and that's in the carbon spectrum. There is another carbon at 167, chlorine, at 167 ppm. All right, now, your chemical shift tables and stuff. You really do want to have that information, readily available, 167 ppm. This is just slapping you in the face again. That is almost certainly the carbonyl of the ester group. And so there's another puzzle piece. I look over what I've written up here. Oh my, 1, 2, 3, 4, 5 protons, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7 carbons. There, I think we'll stop there. And there are your puzzle pieces. The task now, of course, is to put these together into a viable molecule that doesn't violate any organic chemistry rules. So, that's how you approach doing this sort of thing. What I'm going to do is apply the magic eraser, and I'm going to move on to the other big unknown in this Friday assignment, and that is the research lab unknown. So let me apply the magic eraser and be right back. And now the unknown from the research, from one of the research groups. I like using these from time to time simply to give a feel for how NMR is used here in the research labs to solve sometimes simple and sometimes some more complex type problems that the various research groups encounter. This one was a molecule they're trying to confirm the structure of before they made use of it in a further synthesis project. It also illustrates a couple of facts that we've talked about in NMR. As presented when we acquired the spectrum, the carbon spectrum was not a very clean one at all. This was not a terribly concentrated sample, and that natural abundance issue, only 1% of our carbons are actually magnetic. So when we run a carbon spectrum, our concentration drops by, a factor of 100, essentially. Meant that the carbon spectrum was very noisy. The students who took it could have used more scans to increase the signal to noise, but this is the spectrum we had. For our purposes in learning how to interpret, I went ahead and created a simulated carbon spectrum. That's the second one that you see in here, just to make it a little bit easier to look at and interpret, so some of the noise doesn't become distracting for the students here. So again, we start taking an inventory of the pieces using our number of groups and integrations. That's where I usually like to begin. This particular set of spectra seems to have 4 hydrogen groups, groups in there, and they have an integration of 5 to 2 to 2 to 3, 5, 6, 7, 8, 9, 10, 11, 12. 12 hydrogens seem to be in this molecule. Now, I'm going to go ahead and look at the number of carbon groups as well. I seem to have 9 carbon groups, so at least 9 carbons, and by symmetry, maybe even more than that. So this is a fairly substantial molecule. We start looking at the chemical shifts, and one of them should just come right out and slap you in the face, and that is we have 5 hydrogens at 7.4 ppm. Okay. Once again, our dear friend, the substituted benzene ring. Now, a couple of things about it. On the previous set of spectra we looked at, the basic unknown, the aromatic region was kind of nice and distinct. It wasn't a clump of 5, it was 2, 1, 2. There, the hydrogens in the aromatic ring were nice and distinct from each other, the ortho, meta, and para positions. In this particular sample, the ortho, meta, para positions all seem to be overlapped with each other. And so, it's not unexpected. So we have a group of 5 instead of a group 2, 1, and 2. Overlap is a notorious issue in carbon spectra, or in proton spectra. Carbon sometimes, proton much more often. So here's an example of it, but it's not that much of a hassle. And then, of course, if we assume an aromatic ring in here, you do want to confirm it. Look for the evidence of the aromatic ring in the carbon spectra, and sure enough, we do. There are 4 carbons in this spectrum, all at chemical shifts of 120 to 140 ppm, which is exactly what you would expect to see for an aromatic ring like that. So, again, inventory of the pieces. Here's one of them. One of those things again, and some other stuff attached out here. Okay, so have that down. Now we have a group of 3 hydrogens at, and this one was at about 2.2 ppm. Okay, now 3 hydrogens, ding, methyl group likely 2.2 ppm. Now methyl groups are at somewhere in the neighborhood of 1 tend to be methyl groups at the end of a chain. Methyl groups, higher than that, here in the 2.2 region. Remember, that's a messy region of a proton spectrum. There's a lot of stuff that comes there. But things that integrate to 3 in that 2.2 region, it's almost certainly a methyl group. But a methyl group next to something, and I usually phrase it, something interesting, not just another CH2 group on it that makes it the end of an alkyl chain. The interesting thing could be a carbonyl, or it could be the benzene ring. Now, to stick the methyl group here at the end of the benzene ring means there, the molecule's done. And, you know, clearly the molecule's a lot larger than that. So I'm going with a carbonyl possibly. If I'm going to propose a carbonyl, I had better find a carbonyl in the carbon spectrum. So I'm going to look up that in the, in the downfield side of the carbon spectrum. And surprisingly, I actually find two. I find one carbon at, 203 or so ppm. Certain, that's almost a dead giveaway of a ketone. But I see another carbon at 168 ppm, which is virtually exactly the same as in the previous example, carbonyl group of an ester. So we have actually these two different groups, almost certainly going on in here. And so CH3 probably next to some sort of carbonyl. Don't know which one it is yet, but we do seem to have a ketone in here. We do seem to have an ester in this thing. So there's a couple more of our pieces that we've kind of added to our inventory. Now, we also have, there it is, two hydrogens at about 3.5 ppm. Okay, now 3.5, it's a little bit on the low side, but it's in the neighborhood, 4 plus or minus about a half either way. This is pretty, this is pretty clear evidence that we have a CH2 group, and it's likely near something electronegative, most commonly an oxygen. So I would venture to say we have that in there. And sure enough, if you look at the carbon spectrum, sure enough, there is a carbon just a little above 60, much like in the previous one and previous unknown. So I'm going to add that to my collection of puzzle pieces that I'm going to put together. And then finally, I have one last one, two hydrogens at 5.1 ppm. Now 5.1, that's interesting. 5.1 is usually the range where we start thinking about alkenes. 5 to 7 is the alkene range in a proton spectrum. And this is, at 5.1. So, my first thought when I first saw this spectrum, my first thought was, oh, well, we must have a carbon-carbon double bond with, maybe, these two hydrogens on it and, other stuff over here. But as we always do, we want to, if we propose a ketone, we look for the carbonyl signal in the carbon spectrum. If I'm going to propose an alkene, I had better find those two carbons in the carbon spectrum. And so take a quick glance at the carbon spectrum for a moment and realize there are no other carbons in that, 110 to 140 ppm range, where carbon alkene and carbon aromatic rings do tend to overlap each other. They do tend to, come in the same chemical shift range pretty much. But in that area, there are only 4 carbons in the, 110 to 140 ppm range, and they're already accounted for. They're the benzene ring. There are no other carbons there. And so while this chemical shift, kind of makes me think about an alkene, looking at the carbon spectrum makes me think, nope, I don't think that is one of my puzzle pieces. So you have to think of other ways to get a set of hydrogens all the way up here at 5.1 ppm. I wonder if you combined some of these effects. Well, anyway, okay, we'll think about that. So we have a CH2, another CH2, separate from this one, that is up at 5.1 ppm. I'll mark that one, which means there's interesting stuff around it, maybe more than just one oxygen. Well, anyway, so looking at our puzzle pieces here, I do see that I have 1, 2, 3, 4, 5, 6, 7, 8, 9 carbons, distinct carbons here. Cool. I have 5, 6, 7, 8, 9, 10, 11, 12 hydrogens. How interesting. And so, this seems to be the collection of puzzle pieces that we have to work with. Get at it. Have fun with it. Remember, it's due on Friday by the end of the day. And email me any questions if they come up. Otherwise, have a good one.